Okay, so let's get started. We're going to be taking a look at setting up our fuel pressure compensation in our Link G5 and G4X programming. Now, our fuel pressure compensation is going to allow us to track where our fuel pressure is at and compare it against our manifold pressure and be able to calculate what's known as a differential fuel pressure or the base pressure of your fuel system. Now, the reason why we want to track this, because in the modeled mode, we're actually able to compensate for the injector flow and the injector dead time based on the base pressure changing. So for example, if you tune the engine at 300 kPa of differential or base pressure, and then you adjust your regulator to 400 kPa of differential base pressure. So you're doing a fuel pressure change on your fuel pressure regulator. You don't have to go back in and retune everything. It's going to automatically compensate for you. Now, likewise, if you're at high RPM, let's say you're at high load, you're going in, you turbocharge the engine, and you get some fuel pressure drop, maybe your fuel pumps aren't keeping up. With the fuel pressure compensation, you're able to go in, not have to really touch anything, and the Link will automatically calculate the fuel pressure drop and increase your injector pulse width to compensate. Now, that's not ideal, meaning we don't want to keep it like that long term. We want to be actually solving the fuel pressure drop. However, it won't allow the engine to run lean. So it's really, really key to set this up, in my opinion. For the cost of a fuel pressure sensor, it's under $100. Wiring it in is pretty easy. You definitely want to take the steps to always integrate a fuel pressure sensor. Let's talk about how we can do this and how this actually works and the idea behind our differential fuel pressure. So coming up on screen, I want to talk about that first, just the basic and fundamentals here. We're going to talk about our differential pressure. What we're going to find here is that in the first picture, we're going to see that we have our fuel rail, we have an injector, and then the injector would be mounted in the intake port. So it's just kind of a generic look at what I want to illustrate here. So in this first example, this would be a returnless style fuel system that runs a consistent fuel pressure. So the fuel pressure is fixed. We don't have an external fuel pressure regulator that's vacuum referenced. So this is typical returnless system on a new modern car. In this situation, we're going to find that we have 45 PSI of fuel rail pressure. Then at the intake port, let's say the engine is idling and pulling negative 10 PSI of engine vacuum. In this situation, the differential fuel pressure will be calculated at 55 PSI. So it's always going to be, in this case, the fuel rail pressure minus the intake port pressure. In this case, negative 10 PSI. We have a negative and a negative that turns to a positive mathematically, and we find that it adds together. It's going to be accumulating. So in this situation, our differential pressure would actually be 55 PSI. Now, why does that matter? We've talked about this before when we're specifying down here the rated pressure and the flow of the injector. This is important because the Link is going to be calculating from this. So if your differential pressure changes, then technically speaking, the flow rate through the injector is going to change, and the Link needs to be able to compensate for that. So right here, we should understand vacuum in the intake port, fuel pressure in the rail is 45, differential pressure is calculated in a returnless system as 55 PSI. It's going to be fuel rail pressure minus manifold pressure. That's where it gives us 55 PSI. All right, next picture here, we're going to find fuel rail pressure still at 45. We haven't changed that. Again, constant rail pressure in a returnless system. And now we're going to find ourselves at atmospheric pressure or 0 PSI. So again, fuel rail pressure, it's going to be plus the intake port pressure. So that would give us a total differential pressure of 45 PSI. So the fuel rail pressure hasn't changed, but now the flow through the injector has changed. All right, taking a look here at the next example in a returnless system. Again, rail pressure is constant at 45 PSI. Now we're going to introduce 10 PSI of positive manifold pressure in the intake manifold going into the engine. Because it's fuel rail minus manifold pressure, we're going to find 45 PSI in the rail minus the intake port pressure, 10 PSI, gives us now a differential fuel pressure of 35 PSI. So now the flow through the injector is changing a decent amount in this returnless system. When we're going in here in our fuel system type and we're selecting it, whether it's map referenced or in the returnless option, it needs to know this in order to be able to calculate that differential fuel pressure based on what we have in our fuel system. So this sets up the calculation. Again, it's taking a look at the manifold pressure here, and it's going to be also taking a look at then what the fuel pressure or the injector is rated at. When we select either of these options, we don't have a fuel pressure sensor integrated. So hopefully that's clear. So in the returnless option, that's going to be what it takes a look at. And then it recalculates what the injector is actually flowing to calculate your base injector pulse width here. So the effective pulse width, that's your base pulse width. It needs to know what the fuel system type is in order to calculate this correctly. Okay, so hopefully that makes sense. Now,
thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here. And you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.